Okay, this is related rates problem number 5, and we're talking about a train traveling zero point 0.8 kilometers per minute along a straight track. So right here is our train traveling. It's traveling in this direction right here, okay? So there's our train traveling. And it's moving in a direction shown. A movie camera, which is down here, which is 0.5 kilometers away. So right here, this is kilometers away from the track, is focused on the train. So the camera's going to focus, and then as the train moves, the camera's going to rotate and follow the train, okay? And if they gave us that the train is traveling 0.8 kilometers per minute, they gave us a rate, and in our picture this is called x. So we're going to say dx dt, which is in kilometers per minute, is going to be 0.8 kilometers per minute. So they just gave us dx dt. Okay, now they said express the distance between the camera and the train as a function of x. Well, we know this is 0.5, so they basically want to know what this distance, and they're calling it z. I don't really like it that they call it z, but in this problem that's what they're doing. So we want to know what that is really called. So if I were to look at what this distance would be, I'd say this is a right triangle. I could say x squared plus y squared, and we'll call this y if you will, which is a constant because it's 0.5, equals z squared. Okay, so when I go to do this, I say, okay, x squared plus 0.5 squared equals z squared. So in this case, if we were going to represent what z is, if I took the square root of both sides, z is represented as the square root of x squared plus 0.25. So that's really what that is represented in terms of x. Okay, so that's the first thing I wanted to know. And we did that, so it's right here. Now, basically what they're doing in this problem is taking it through step by step, where sometimes in class we go through the whole thing. So let's look at this next one. It says, how fast is the distance from the camera to the train changing? Okay, so here is the camera. Don't forget it's right down here. And we want to know how fast the distance from the camera to the train is changing. So we really want to know what dz dt is, because that would be that distance. That's what they're asking for in this question. Okay, and they said when the train is 1 kilometer from the camera. So they're basically telling you that z is 1 kilometer, so we can put that in our picture here. And then we can say, all right, we need to find dz dt, but we got to know what the relationship is. So I know that x squared plus y squared equals z squared. And if we take the derivative of that, it's going to be 2x dx plus 2y dy equals 2z dz. And then I'm going to go through and divide through by dt because everything's with respect to time. And another cool thing is because everything's multiplied by 2, we can go back and divide it all by 2 so that you can see that it's really a nice equation here. So I can say thanks for playing, all right? And the other thing we can say is, all right, if we look at this picture here, the camera is stationary right here. Here's the camera, okay? What's constant is going to be y, because they're not going to move it. The camera's just going to rotate. It's going to rotate this angle theta. It's going to start shooting here, and then as the train moves, the camera's going to rotate to the right to follow the train. Okay? So in all, we know that y is 0.5. We know this is 0.5 kilometers, but dy dt is essentially 0 because the camera's not moving. So our new equation actually comes out to be x dx dt equals z dz dt, which is a lot nicer to work with. All right. So we know the x, or no, we don't know the x yet. We know everything else. We know what dx dt is. We know what z is, and we're looking for dz dt. So we got to find out what the x is. Well, the x is going to be at that moment when it's 1 kilometer. So we're going to say x squared plus, we know the y was 0.5 squared equals 1 squared, and this is kind of what we did in the first one. So we know that x squared is going to equal 0.75. When I subtract that, take the square root, x equals 0.866, Or we can look at it this way, x squared plus 1/2 squared, that's what 0.5 is, equals 1 squared. And x squared plus 1/4 equals 1. X squared equals 3/4. And take the square root of both sides. X equals radical 3 over 2. Now the reason why I did this, and I actually prefer this one over this, is because this is rounded and this is not. And I know that's a more exact value and it'll probably give us a better answer. Okay, so I'm going to go back to the problem, and let me change back to black here, and I'm going to actually put everything we know. So I know x at that time is radical 3 over 2. That lets me right here. Sorry about that. Let's see if I can get this in here. There we go. Radical 3 over 2 times d, and this is going to be in kilometers, times dx dt, which we knew was 0.8 kilometers per minute because they told us that earlier in the problem, equals z, which we know is 1 kilometer, times dz dt. And this is what we're solving for, is dz dt. And how nice is there's a 1 on that side. So once I multiply the left, I'm going to find out what dz dt, and dz dt is going to be is going to be 0.693 kilometers per minute. Now I'm happy that this is positive for a couple reasons. Let me highlight this first. I'm happy this is positive because I know that when this camera is rotating right here, that this distance is going to be increasing because the train is moving to the right. So I knew that it should be positive, and it worked out so great. Okay, now we want to know how fast is that camera rotating. So we're just looking at that camera. And the biggest thing when we try to do these is try to figure out what what trig function to use. So I'm using here, we had an x here, and they gave us y. They told us y right here was 0.5. So I look, that's opposite over adjacent, so we're going to use tan. So you always use what they gave us and what is actually moving that camera is rotating about. So I'm going to do the tan of theta is opposite over adjacent, which is 0.5, which I can really write that as, because x divided by 1/2 is actually 2x, which is a lot nicer. All right. Now I'm going to take the derivative of this. So the derivative of tan is 1 over cosine squared, or secant squared, they both work. 1 over cosine squared theta d theta equals, and if I take the derivative of 2x, it's 2 dx. Go through and divide by dt. And I'm solving for d theta dt, so if I multiply both sides by cosine squared, I get d theta dt equals 2 cosine squared theta dx dt. And then we can actually just kind of plug in everything that we know. So we know that d theta dt equals 2 times cosine squared theta. Now cosine squared, okay, if we were to look at this angle right here, let's go back, oops, sorry. Here, cosine of this angle right here is adjacent over hypotenuse, and we know the hypotenuse is 1, so let's go back down where we were. So that actually just comes out to be a plain old 0.5, which is nice for us to use. So that's 0.5 squared, or 1/2 squared. And then dx dt is 0.8. Okay, so now I know that d theta dt is going to be 0.4 radians per minute. And that concludes this problem with the train.